Welcome back to The Explainer. Today, we're going to completely dismantle our everyday common sense understanding of a predictable, rock-solid universe. Using some truly fascinating source material, we are going to peel back the curtain on reality itself and discover that the universe is actually far stranger and honestly far more beautiful than we probably ever imagined.
Okay, let's dive right into this. Picture this. You're hanging out in the park, and you throw a baseball to a friend. How many paths does that ball take to reach their glove? Well, common sense, and centuries of classical physics for that matter, tells you it takes exactly one path. Just one single, well-defined trajectory through the air. But what if I told you that is the most convincing illusion nature has ever devised? What if that ball is actually exploring literally every possible path, all at once?
Here's our roadmap for today. 1. The illusion of one path. 2. Waves, particles, and uncertainty. 3. Taking all possible paths. 4. Superpositions and spooky connections. 5. The quantum world around us. And 6. How reality finally solidifies.
Starting with Section 1, The Illusion of One Path, Rethinking Classical Certainty. So our everyday world is totally governed by classical physics. It's this world of solid billiard balls, right? Where causes always precede effects, and objects just follow predictable, single paths. But as our sources so vividly describe, when you zoom way, way down into the deepest workings of matter, that classical certainty totally vanishes. It's replaced by this probabilistic fog. It's a shimmering landscape of possibilities where objects actually explore infinite paths at exactly the same time.
And this analogy perfectly captures what we're talking about. Think of a lifeguard on a beach trying to reach a drowning swimmer. The lifeguard doesn't just run in a straight, direct line to the water, do they? No, they run further on the sand first because they can run a lot faster than they can swim. They optimize their route to minimize the total time. Well, our sources reveal that light and really all quantum particles do the exact same thing. But here's the catch. A particle doesn't have a brain to calculate the fastest route. So how on earth does it know where to go? It turns out it doesn't just choose one path. It takes all of them.
Section 2. Waves, Particles, and Uncertainty. Breaking the Rules of Physics.
Now, the unraveling of classical certainty didn't happen overnight. It happened in a few really monumental leaps. Back in 1899, Max Planck fixed a massive mathematical nightmare by proposing that energy comes in tiny indivisible packets called quanta. Then, in 1905, Albert Einstein took this even further, proving that light itself behaves as these discrete little particle packets, or photons. And by 1926, Erwin Schrödinger comes along and formulates an equation describing these particles not as solid little dots, but as rippling waves of probability.
This wild wave-particle duality leads to what one of our sources actually calls an embarrassingly simple setup, the famous double-slit experiment. You literally just shine light through two tiny slits in a piece of cardboard. If you fire single photons, one by one without measuring them, they act like waves. They interfere with themselves and create a striped pattern on the wall behind them. But, and here's the crazy part, the very moment you put a detector at the slits to see which path the photon takes, that interference just vanishes. The mere act of observation forces that shimmering wave of possibilities to just collapse into a normal, well-behaved particle. Reality, it seems, really does care if it's being watched.
Now, what's really fascinating here is that even the absolute greatest minds struggled with this concept. Albert Einstein absolutely hated this probabilistic weirdness. I mean, he firmly believed the universe had to be predictable and orderly, which led to his famous declaration that God does not play dice with the universe. But, as the experiments kept showing, the dice were definitely rolling.
Moving on to Section 3, Taking All Possible Paths, Richard Feynman's Quantum Secret. Enter Richard Feynman. He demystified all this daunting math into a brilliant, easily visualizable concept. When a particle goes from point A to point B, it literally takes every possible path simultaneously. Some paths go straight, while others might loop all the way to the moon and back. For each of these paths, you calculate something called its phase, which is tied to its energy over time. Imagine every single path has a tiny little stopwatch spinning around. For the wild, crazy, inefficient paths, the stopwatches point in totally random directions, completely canceling each other out through destructive interference. Ultimately, only the paths closest to the optimal, most efficient route constructively interfere and survive.
Let's look at how this plays out in a real-world experiment detailed in our sources.
Normally, if you shine a laser at a mirror, you only see it reflect off one specific point, right? But if you place a specially crafted piece of foil over the mirror, a diffraction grating, that physically blocks out the specific paths that normally cancel each other out, suddenly you can see the laser reflecting off the entire surface of the mirror. It's wild. This proves definitively that light really is exploring every single path across the whole mirror all at once.
Which brings us to Section 4, Superpositions and Spooky Connections, the math that defies logic. So let's talk about superposition. Think of a spinning coin. When it's up in the air, just blurring in the light, is it heads or tails? In the classical world, it's already one or the other, we just don't know it yet. But in the quantum world, a particle in superposition isn't secretly decided. It is genuinely, physically a blend of both outcomes at the exact same time. That fog of possibilities only snaps into a single reality the instant you actually measure it. Next up is quantum entanglement. Imagine you have a right and a left glove. You put them in separate boxes and you send one to Tokyo and one to Paris. Obviously, if you open the Paris box and see a left glove, you instantly know the Tokyo box has the right glove. That's just classical logic. But quantum entanglement is far stranger than that. These particles are like gloves that don't even have a handedness until you look at them. They exist in a shared superposition. But the very moment you measure the particle in Paris, the one in Tokyo instantly snaps into the corresponding state. No signal, no delay whatsoever. This instant, faster-than-light connection made Einstein so uncomfortable he famously dubbed it spooky action at a distance. He figured there just had to be some hidden variables, some secret script the particles were following all along. However, impartially speaking, decades of modern experiments have definitively proved the quantum math right. The entanglement is very real. Our universe is just deeply, instantaneously interconnected in ways we're still wrapping our heads around.
Section 5. The quantum world around us, from micro-weirdness to macro-reality. You might be wondering, why does this matter to us? Well, we are already harnessing this stuff. Quantum computers use qubits hovering in superposition to process vast amounts of data simultaneously. Over in biology, migrating robins might actually navigate using entangled electrons in their eyes, and plants use quantum pathways to heavily optimize photosynthesis. And then there's quantum tunneling, where particles literally ghost right through solid barriers. Without tunneling, the sun simply wouldn't have enough energy to shine, and we wouldn't have the ultra-precise microscopes used in modern labs today.
Furthermore, even nothingness itself is quantum. The quantum vacuum isn't some empty, boring void. Our sources describe it as a restless, humming stage where virtual particles are constantly popping in and out of existence. And we know this is real because of the Casimir effect. If you put two tiny metal plates incredibly close together in a perfect vacuum, the quantum jittering outside the plates is actually stronger than the jittering inside, physically pushing the plates together. Mind-blowing, right? Empty space actually has substance.
And finally, Section 6, how reality finally solidifies, escaping the probability fog.
So all of this leads us to the ultimate million-dollar question. What actually takes that quantum wave of infinite, shimmering paths and collapses it into a single, concrete reality? Well, physicists hotly debate this, generally leaning on two main theories. First is the Copenhagen interpretation, which says that the mere act of measurement or observation extracts information, forcing the universe to pick a definitive state and collapsing the wave function. The competing idea is the many worlds interpretation, which throws the whole concept of collapse right out the window. It argues that the universe simply splits, so when a quantum coin is flipped, it lands heads in this universe and tails in a newly branched parallel universe. Both theories mathematically work, but as you can see, they present wildly different views of reality.
But practically speaking, the real reason you don't see shimmering superpositions in your everyday life is due to a process called decoherence. You see, quantum states are incredibly fragile. The moment a quantum system interacts with its messy, noisy environment, like bumping into air molecules, heat, or light, the superposition gets filtered out and tangled up with the environment. It effectively breaks the spell, making the macro world appear strictly classical. That is exactly why your cats, your cars, and your coffee mugs stay wonderfully, predictably solid.
Let's end on this incredibly thought-provoking quote from our sources. The universe at its core is not a clockwork machine. It's a strange and shimmering tapestry woven from possibilities. It really leaves you wondering, doesn't it? Is the universe simply a library of endless potentials, quietly waiting for you to just look at it? Thank you so much for joining me on this explainer. Keep wondering, keep observing, and I'll catch you in the next one.